Welcome to a tribute to Dorothy Crowfoot Hodgkin, a pioneer who decoded the very blueprints of existence. As the only British woman to receive a Nobel Prize in science, Hodgkin mastered the intricate art of X-ray crystallography, revealing the complex molecular structures of penicillin, vitamin B12, and insulin. The image highlights her dual legacy, a brilliant scientist captured for life by chemistry and by crystals, and a dedicated humanitarian who forged lasting human bonds. By mapping the invisible architecture of life, she didn't just advance medicine. She bridged the gap between scientific discovery and global peace. This is the story of a master architect who shaped our understanding of the chemical world. In 1964, the media painted a reductive portrait of a housewife, winning a Nobel Prize. But as our slide illustrates, the fiction of an affable-looking Mrs. Hodgkin stands in stark contrast to the reality of her monumental scientific achievements. In truth, Hodgkin was a towering figure in structural biology and protein crystallography. She remains the first and only British woman to win a Science Nobel, earned by solving the complex molecular puzzles of penicillin and vitamin B12. Far from just a domestic figure, she was a medical savior whose work enabled the mass pharmaceutical production that has saved millions of lives worldwide. Her legacy is one of unparalleled intellectual rigor. Dorothy Hodgkin's journey was a parallel pursuit of scientific clarity and global harmony. Born in Cairo in 1910, her worldview was forged by the fractured world of World War I. The loss of 4 uncles and her mother's pacifist activism instilled in her a lifelong commitment to international peace. Simultaneously, the scientist emerged. By 1920, she was growing crystals in primary school. In 1923, she used a surveyor's kit to analyze minerals from Khartoum. And by 1925, a transformative book by W. H. Bragg revealed that X-rays could see atoms. This timeline illustrates how Hodgkin's early life synthesized a rigorous analytical mind with a deep humanitarian soul, seeking to find order in both chemical structures and human society. This slide illuminates the rigorous 3-step process of X-ray crystallography, the methodology Dorothy Hodgkin used to visualize the invisible. The target, organic molecules, are painstakingly coaxed into a purified, regular crystalline structure. The scatter, an X-ray beam, is fired at the crystal, deflecting off individual atoms to create a 2D diffraction pattern of dark spots. The blueprint, through complex mathematical decoding, transforming scatter angles and intensities. A precise 3D map of atomic bonds is revealed. As our narrator, I invite you to see this not just as chemistry, but as a bridge from abstract data to the physical reality of life's most essential molecules. This slide explores the revolutionary shift Dorothy Hodgkin brought to structural science. While traditional chemistry relied on the blind guess of tedious chemical reactions and degradations to infer a molecule's shape, Hodgkin introduced a gifted intuition that allowed her to see what others could not. Collaborating with J. D. Bernal in 1934, she captured the first X-ray of the pepsin protein, realizing biological molecules could be mapped directly by utilizing the heavy atom method. Using iodine and cholesterol as a reference point, she anchored complex electron density calculations. This effectively allowed her to draw the molecular skeleton, transforming biology from a game of chemical shadows into a precise, 3-dimensional reality. This slide visualizes Dorothy Hodgkin's relentless ascent through the molecular world, charting her progress as she tackled increasingly massive structures. Starting in 1945 with penicillin, approximately 39 atoms, she moved to the daunting vitamin B12, 181 atoms, in 1956, and finally to the monumental insulin, 788 atoms, in 1969. As the atom count exploded, so did the mathematical burden. Hodgkin proved her adaptability by becoming an early adopter of advanced computing. She transitioned from labor-intensive hand calculations to utilizing analog and early digital mainframes, like the SWAC, to process the thousands of equations required for her maps. Her journey reflects a perfect fusion of biological insight and computational pioneering. This slide showcases Dorothy Hodgkin's crowning achievements, 3 molecular breakthroughs that redefined modern medicine. In 1945, she solved the penicillin problem, proving the existence of the unstable beta-lactam ring, and enabling mass production of antibiotics. By 1956, she decoded vitamin B12, discovering a unique cobalt-centered corrin ring that turned fatal pernicious anemia into a treatable condition. Finally, after 35 years of persistence, she revealed the insulin hexamer in 1969. This discovery, centered on zinc stabilization, revolutionized diabetes care, and paved the way for synthetic insulin analogs. Together, these structures represent a portfolio of persistence, where complex chemical mapping has directly translated into saving millions of lives across the globe. This slide details the Herculean effort required to solve vitamin B12, a molecule so complex it was considered a structural sound barrier. Containing over 180 atoms and a central cobalt atom, the challenge demanded a technological leap. Long before the Internet, Hodgkin orchestrated a pioneering transatlantic collaboration. She dispatched punch card data via telegraph and mail from Oxford to Kenneth Trueblood at UCLA. There, the data was processed on the SWAC, the world's fastest digital computer at the time. This remote partnership led to the discovery of the corrin ring, a breakthrough that earned her the 1964 Nobel Prize. Lawrence Bragg aptly described this feat as an achievement equivalent to breaking the sound barrier in chemistry. This slide chronicles Dorothy Hodgkin's enduring North Star, the 788-atom insulin globulin protein. Her journey began in 1934 with the first X-ray photograph of an insulin crystal, but the technology required to solve such a massive structure didn't yet exist. Through decades of persistence, Hodgkin refined X-ray techniques and embraced evolving computing power. Finally, in 1969, leading a young international team, she revealed the 3D map of porcine insulin. This breakthrough allowed scientists to observe exactly how insulin interacts with receptors, directly enabling the development of the synthetic insulin analogs that millions of people with diabetes rely on today. It remains a testament to her lifelong dedication to medical science. This slide reveals the profound personal resilience behind Dorothy Hodgkin's scientific triumphs. At just 24, she was diagnosed with severe rheumatoid arthritis, a condition that threatened the very manual dexterity her work required. Yet, Hodgkin's spirit remained unbound. In a remarkable display of adaptation, she engineered custom physical aids, such as extra-long levers for X-ray switches, to accommodate her swollen and distorted joints. Despite the pain, her drive never faltered. She continued executing microscopic manipulations of crystals and maintained a rigorous global schedule of science and diplomacy from a wheelchair well into her 70s. Her legacy is not just one of intellectual brilliance, but of an iron will that refused to let physical constraints limit her contribution to humanity. In this final slide, we see how Dorothy Hodgkin translated the symmetry of molecules into a framework for world peace. Guided by the mission that international conflict, like chemical structures, could be resolved through logic and evidence-based cooperation, she bridged the gap between science and diplomacy. Her Pugwash leadership saw her serve as president of the Pugwash Conferences from 1976 to 1988, an organization that later secured a Nobel Peace Prize. Using the method of untouchable prestige, she bypassed traditional political barriers, uniting global scientists to advocate for nuclear disarmament and war prevention. For Hodgkin, the quest for crystal harmony was never confined to the lab. It was a blueprint for a unified, peaceful world. This slide illustrates Dorothy Hodgkin's remarkable ability to use scientific prestige as a tool for high-stakes diplomacy. During a 25-year gap, 1960 to 1985, when Chinese scientists were largely isolated from the international community, Hodgkin acted as a vital node for global connection. Leveraging her academic standing and personal networks, she established unofficial backchannels with figures like physicist Zhou Peiyuan. By connecting the UK to the USA, the Soviet Union, North Vietnam, and China, she proved that scientific solidarity could pierce the Iron Curtain. Her quiet persistence culminated in China's formal re-engagement with the Pugwash conferences in 1985, demonstrating that the pursuit of truth knows no political borders. This slide reveals how Dorothy Hodgkin's influence transcended the laboratory, reaching the highest levels of global power. At a remarkable historical intersection, future Prime Minister Margaret Thatcher studied chemistry as an undergraduate under Hodgkin in the 1940s, working on the crystallography of gramacydin C. Despite being total ideological opposites, Hodgkin a socialist peace campaigner, and Thatcher the face of Western conservatism, they shared a profound mutual respect. Thatcher famously hung Hodgkin's portrait in 10 Downing Street. Hodgkin leveraged this unique connection to lobby Thatcher on nuclear disarmament, even encouraging her pivotal visit to the Soviet Union. This relationship exemplifies Hodgkin's legacy, using the shared language of science to foster human connection and thaw the coldest of political relations. In this summary, we see the true core of Dorothy Hodgkin's genius. Whether she was untangling the 788-atom knot of insulin to heal the human body, or navigating the jagged geopolitical factions of the Cold War to heal the world, her work was guided by a single, unwavering philosophy. She believed that there is an underlying structure to all things, no matter how chaotic they appear on the surface. With immense patience, empathy, and observation, the invisible bonds that connect us, chemically and humanly, can always be revealed. This slide serves as a powerful testament to a woman who found order in the infinite, leaving a legacy of both scientific truth and global unity. In our concluding visual, we reflect on the complete map of Dorothy Crowfoot Hodgkin's life. It was a journey that transitioned from the microscopic, solving the chemical riddles of penicillin, vitamin B12, and insulin, to the macroscopic, where she navigated the complex structures of global diplomacy and peace. This presentation has shown that Hodgkin's greatest tool was her ability to see patterns where others saw chaos. Whether adjusting a microscope with arthritic hands or advising world leaders across the Iron Curtain, she proved that scientific rigor and deep empathy are not separate paths, but a single way of understanding the world. Dorothy Hodgkin remains the ultimate architect of life, leaving behind a blueprint for both medical progress and human harmony.